The Royal Swedish Academy of Sciences has today decided to award the 2018 Nobel Prize in Physics with one half to Arthur Ashkin for the optical tweezers and their application to biological systems. And the other half jointly to Gerard Mourou and Donna Strickland for their method of generating high-intensity, ultra-short optical pulses. Pour moitié à Arthur Ashkin pour la pince optique et son apotические пинцеты и их применение в биологических системах. And you can see now our new Nobel laureates with us. Donna Strickland was born in 1959 in Guelph, Ontario, Canada.
And finally, he took a lens and focused the beam so that he could trap and still keep the ping pong ball under control. And up to 1985. And what you see, there is a first rather important development. And here we will demonstrate what happens if we take increased in amplitude, and finally, in the final step, you compress the pulse so that it has the same duration. The intensity is a little bit lower, and these pulses are adopted to a new field of science called attosecond science.
We may now have one of our new Nobel laureates with us on the phone.
Well, first of all, you have to think it's crazy. So that was my first thought, and you do always wonder if it's real. As far as sharing it with Gerard, of course, he was my supervisor and mentor, and he has taken CPA to great heights, so he definitely deserves this award. And I'm so happy that Art Ashkin also won. I think that, you know, he made so many discoveries early on that other people have done great things with, that it's fantastic that he is finally recognized. Well, obviously, we need to celebrate women physicists because we're out there, and hopefully in this time it'll start to move forward at a faster rate, maybe. I don't know what to say. I'm honored to be one of those women.
Thank you very much. Now the individual interviews, but we'll close this press conference. Thank you. And welcome back tomorrow for chemistry.
The first part of the prize to the optical tweezers has been extremely important for measuring small forces on individual molecules, small objects, and this has been very interesting in biology to understand how things like muscle tissue works, what are the molecular motors behind the muscle tissue. In the second prize, it's reaching these extreme high-intensity fields, which can then rapidly accelerate electrons inside the atom. We can start to discover, we can create very short pulses and start to understand the dynamics of electrons inside the atom, and that's having a big effect on chemistry and understanding matter in extreme conditions. The real-world application there is, for example, laser eye surgery, where this short, intensive pulses of laser are used to cut and open the cornea, and then also to remove material from the cornea to shape it into a lens which is better focused on your retina. And also another application is in machining glass, or what we call micro-machining. For example, when you engrave something, that's done with lasers now, and that is done with this, I'm not sure of exactly this type of laser, but these short, high-intensity pulses.